Up until now, we have only described the properties of a system in equilibrium. However, it is important to introduce what happens to a semiconductor when it is illuminated with light. The process of interest is known as photogeneration of charge carriers. Here, electron-hole pairs are generated as light is absorbed in a semiconductor. During the course introduction, we have already mentioned that mobile electrons and holes are formed in a semiconductor as a result of light absorption. Now, I will explain how this process happens. Here we see a photon incident on a semiconductor. At some point, this photon can be absorbed by the material. Absorption is a process in which the electromagnetic radiation interacts with atoms of a semiconductor, in particular with the valence electrons. This interaction can lead to a liberation of an electron from a covalent bond. If this happens, a valence electron is excited from an energy state in the valence band to an available energy state in the conduction band. It is important to remember that the excitation of an electron to an energy state in the conduction band leaves an unoccupied energy state in the valence band. This state is then occupied by a hole. Photogeneration results in generation of electron-hole pairs, or in other words, the concentration of mobile electrons and the concentration of holes in the material is increased by the same amount. However, this excitation does not always happen. Photogeneration is limited by energy constraints. To understand these constraints, we need to look at the bandgap energy of a semiconductor. As you recall from our previous video on band diagrams, there are no available energy states for electrons in the bandgap. For this reason, only if the photon energy is equal or higher than the energy of the bandgap, the photon can be absorbed and an electron-hole pair generated. However, if this requirement is not met, the photon will simply pass through the semiconductor without being absorbed. You may notice that the photon used in this example is red, whereas the photon that was absorbed in the previous examples was blue. This is intentional. Red photons have less energy than blue photons. In this example, the red photon's energy is less than that of the bandgap, whereas the blue photon has energy larger than the bandgap. But how do we know the energy of a photon? The properties of the electromagnetic radiation emitted from the sun can be described with the help of the wave-particle duality concept. As a wave, this radiation propagates at the speed of light, and it is characterized by two parameters. The first is the wavelength, which we denote lambda. It is defined as the distance between two adjacent wave peaks. The second is the frequency, which we denote nu, representing the number of cycles per second. It is determined as the ratio between the speed of light and wavelength, and it is measured in hertz. However, light can be seen also as a flow of particles, which are called photons. The energy of a photon is directly proportional to the product between the frequency and the Planck's constant h. Let's now apply these concepts to determine the minimum energy that is needed to liberate a valence electron in a silicon wafer. The bandgap energy of crystalline silicon is equal to 1.12 electron volts. This is the minimum amount of energy required for a photon to be absorbed and excite an electron from an energy state in the valence band to an unoccupied energy state in the conduction band. We can now apply the relationships we just saw to determine the wavelength of the electromagnetic radiation corresponding to this energy value. Stop the video now and determine the maximum wavelength that can be absorbed by silicon. Now, let's compare your answer with ours. First of all, we need to determine the frequency of light when having an energy of 1.12 electron volts. We find that this is 2.7 times 10 to the power of 14 Hertz. Then we can calculate the maximum wavelength of light that can be absorbed by silicon. It results to be 1110 nanometers. Now let's see what this means when we want to know which part of the solar spectrum can be absorbed by crystalline silicon. In this figure, you can see the spectral power density of the AM1.5 spectrum in yellow. You can also see the fraction of the spectral power density that can be absorbed by silicon and converted into electricity in a solar cell. This is the brown fraction of the spectrum. The red dashed line represents energy of the bandgap of silicon expressed in wavelength of light. Only the radiation at lower wavelengths carries enough energy to be absorbed and excite an electron in crystalline silicon. Therefore, from the solar spectrum, only the part of the spectrum on the left-hand side of the dashed line can be absorbed in crystalline silicon. You may also notice that not all of the available energy in this part of the spectrum is used for generating electricity by a solar cell. This is due to a process known as thermalization, and you will learn more about this in the light management section of the course. As you can imagine, a semiconductor under illumination will be no longer in an equilibrium state. Once illuminated, the amount of electrons and holes change with respect to the thermal equilibrium values. As these charges are mobile, we have to understand how these charges move around in the semiconductor once they are excited. This will be the topic of the next video.